So basically, these are the 26 that PennyLane currently has up. They recently had a software upgrade as well. I'm not sure how that affected the demos, but these are definitely good starts if that's what you want to do is program in quantum. Okay, so the purpose of the demos is basically to understand and improve the existing applications. So some things are kind of limited by, say for instance, numbers of qubits in simulators. All of these I didn't do on real hardware. It'd just be too noisy in any type of real world application. And you'll find that is on a number of these you should be able to see right now. Okay, so you should see right now it should show the cover screen here as we get more people here. So if somebody could put in the chat, you should be able to see here. It says you're sharing this specific thing. And, basically to improve runtime speeds, and also you want to do both, right? You want accuracy, you want loss, more accuracy, less loss. You also want better runtime speeds, which is lower speeds. So the simulators which I shared here is basically this. It's default.qubit. It's the most compatible of all this bunch. And then you also have, say, lightning.qubit will work sometimes, circ.qsim. I had a good example of a speed up over their circ.simulator. You also have a default.mixed and strawberry fields.foc is their simulator for photonic quantum computing. So most of these are shots equals to none. And what that basically means is it's analytic results is it's getting the exact expectation value right away. In a lot of these workflows, it would take an extraordinary, in my opinion, based on what I know, a long time to run on real quantum hardware because to get to an exact value, you're talking like tens of thousands or hundreds of thousands of shots in many of these cases. So it's not just that, so that's a big obstacle if hardware to come into play with this. And you also have simulators for free and easily. So basically, I didn't pay anything. I paid Colab a little bit just to run these. And I was just using CPU most of the time. I did use GPU just a little bit. And if you can use adjoint differentiation on these, more power to you. So that should help with, I think it's typically time. It makes things run better. So on quantum simulators, you get quantum reversibility with that. And also, so the way I performed all this is basically you have the websites and you can download the Python notebooks, which are .ipynbs. I also printed a PDF just to be safe. And then I had to fix a couple of these demos. There's 4 of them through forums. And then also I had to try Qiskit IDE as opposed to Colab for one. So this is to help you, with your quantum journey and to progress. So notebooks requiring datasets or other files were uploaded via a Colab Drive mount. It's a standard type of thing. And it's for educational purposes only. Modifications may represent portions of the notebook. A lot of times when I put the actual runtimes and I put the actual graphs and these types of things, they're not always representative of the whole notebook. OpenAI was utilized for clarification code and terms for some things. It's a helpful resource. And then better understanding of quantum physics will likely aid all of this. It's still, all of this is kind of like in these demos and you have the papers that go with it, but it'll all, in my opinion, go like this is going to start taking off. And, so especially when you understand qubits and how it's manipulating with data sets, especially those. So number one here is an equivariant graph embedding. Here's the quantum circuit in the middle. And what I did with this one is I just did an adjoint diff method. So you see the time go down from 1.98 seconds to 1.61. And then you also, it's this graph embedding stuff. So numerical representation of a graph in a computer is not unique. So you need to do these methods, to approach these. So feel free to put it in the chat. I mean, everybody should, if somebody could put in the chat if you do see it. So I don't know, George, maybe restart the computer. I'm not sure, but it shows on mine. It's screen sharing. So maybe you know, who else is on here? Okay, so the shared, it's being seen, George, so maybe restart Zoom. And then basically, you know, it gets into this permuting qubit registers in the correct way, as we get more people coming on here. And basically, at the end of this notebook, it gives you 3 values, and the first and the third should match, which they do in my case. It just varies. So the end of this is basically a joint differentiation and QNode decorator decreased model runtime. So you can only put, as far as I know, so the at QML.QNode and Pennylane is called the decorator, a QNode decorator. So for instance, the QNode on itself is called QNode. The decorator is at QML.QNode. And to change differentiation methods, which affects training, which affects, it's essentially the machine learning and the component of the AI behind it, is that you know, you have to do it through the decorator. You can't do it through device, you know, dev equals device, these types of things. So a joint through that. So that's the first one. So after a couple of these, when we get going, we'll stop and have some questions. Feel free to put in the chat. You could also raise your hand as well. Now for the second one, basically is this: improve trained model accuracies. And this is using angle embedding, which is an embedding layer, strongly entangling layers, which is variational layer. Is I actually, and I got this for some of these, is I'm increasing the accuracy without even having to train the model, right? So it's just the quantum circuit, the function on its own is doing better because of the changes being made. In this case, just changing from n equals 1 qubit to n equals 2. So you know, the purpose is this is basically this time series anomaly detection. Now they had an interesting, they call it a time machine for this particular one. You'll see in the upper left-hand corner. And the QBR leverages the power of a unitary time evolution, devolution operators to learn a model or normal behavior. And, you know, some of these the demos are quite long. So you kind of have to grasp as much as you can. There's many types of quantum machine learning out there. So what was interesting about this one is that they are using covalent. So covalent is basically this tool that pulls things together, you know, with different tasks and resources and those things. And also that was the result. So doubling the qubits in this one helped with training. So you'll see a couple of my tactics out there as far as trying to get better accuracy. And then this next one is Introduction to Geometric Quantum Machine Learning. So as you can see at the top is the sacrifice of running a larger quantum circuit on the right is runtime, but you see the accuracy with the green line for my standard, which is the one, you know, a little bit into the notebook, not towards the end, is not the same or as it was before. So accuracies are higher, those types of things. And you also see, so the whole purpose of the notebook is to use symmetry to help things out. So you'll see this involving permutations. So in specific, an RX rotation acting on 1 qubit. And then there's a bunch of examples for this, but if a qubit is in the centered location of a grid, then it can flip around any symmetry axis that you like. And then the operation leaves the qubit invariant. So this is one case, right? So, and keep in mind, so most of these, I think only a handful, maybe like 2 or 3 of the 26 actually do something other than shots equals none. So again, shots equals none is basically, it's a simulator advantage where you get the exact value. You don't have to do probable, you don't have to run a bunch of shots. And as far as I know, in order to do like a classical and, you know, hybrid machine learning workload, you need to have shots equals none, which is in essence infinite shots right away, meaning it gets you the answer. Okay, so that's for that. And I saw some things in the chat, and then also, you know, feel free to unmute yourself, Ron, or you can come on as well.
Are you hearing me? I'm having a problem with that 0 shots thing.
Yeah, it's basically the way that if you go on like the PennyLane forums, is you're getting the exact expectation value. So as far as I know, the every quantum device, like real hardware, it's probabilistic by nature. So when it outputs a 0 or 1, it's not always the correct value. So that's why you have to run so many.
Right,
So
right. But on a simulator, if your final result is in a superposition, the simulator has to simulate those probability distributions, right?
yeah, it's just like if you ran an infinite number of shots on any hardware, that this, a quantum device is probabilistic by nature, is that eventually you'll get to the correct answer. Okay. So for some applications with, real quantum computers, it would make sense. But in a lot of these workflows, like we're talking like mini batches and batch size and epochs and those types of things, the way it was described to me is basically in many cases, you want infinite shots right away or shots equals none. So this is getting your exact answer right away. So you don't have to, use so much time like on a real device. And plus you have noise too. So there are applications in quantum machine learning where, that's not the case. And there's a couple here where they do shots equals 1 or shots equals 1,000, where it's not the exact expectation value right away. It's more like it's trying to mimic the results that you'd have on a real device.
I would have to see the mathematics on that because again, if the state of your quantum register winds up with, not being in pure basis states, the measurement is going to collapse those states based on the statistical
Yeah.
distribution.
So I'm not sure
So
if there's
I don't see how you can do that in one shot. So
yeah,
it
single shot.
must be some
Exactly.
magic they're doing
Yeah.
behind the scenes to do something else. But even on a simulator, you can't live with one run. If it's using like a random number generator to generate your measurements based on the distribution
Yeah.
parameters.
Yeah. I mean, that's my take on it with the PennyLane stuff. I'm not sure what the equivalent way of doing it in Qiskit is, but basically, you know, they call it analytic mode. So there's a couple ways of describing it, but basically it's an advantage of not having to output a probabilistic result. It's an exact answer right away.
Yeah, but like I see somebody put in the chat, shots equal none is an exact state vector algebra, but what happens if the thing comes up with 1/√2 as your output?
Yeah, I mean, and this is a conversation we can have too, because it runs the quantum circuit and it's giving the exact value right away. I mean,
Yeah, I'm just gonna assume they're doing something behind the scenes to speed things up, but I don't think it's shots equals 1 or it's just one pass. That's just some way that they're accelerating the process. All right, enough of that.
anybody else at this point before we go on to, so this would be 4. Feel free to raise your hand. You could also put in the chat as well. And any questions along the way too, because I mean, if you want to program in quantum machine learning, this is probably an easier way than with Qiskit. I mean, there's I think 3 or 4 different classes, but this, like for PennyLane, they solely focus on QML. So this next one is basically a convolutional neural network. So it's a quantum convolutional neural network, and it's basically looking at generalization, which is typically it's the comparison between the values like from training and losses from training and losses in testing. So on this specific one, what they're claiming, this is actually I think this is a Los Alamos National Lab paper. And what they're saying is with this 80 samples, so in this chart up here, up and to the left, is it only took n equals 80 to get close to 100%. So they said 97% right away. And then, so this is after, n equals 80 samples, so 80 pieces of data. And then also, after 100 epochs, like running it through this. So what I saw for this one is basically in the upper right is I took out the icings and it actually helped when the data was lower. Okay, so in this chart here, so you have n equals 2, I think you got 5 and 10. So these are all greater accuracies than over here. But as you increase the number of pieces of data, is the accuracy trends towards having this complete full circuit, like this icing circuit with lots of entanglement, these types of things. And then so that's basically it for this one. Is there's many ways of thinking about quantum circuits, and say for instance in this one, you know, for one set of data, it would make sense to you run a smaller circuit, and then for another one run the original circuit, and that's if the original one wasn't working well. So this one in specific was interesting. So all of these terms like quantum singular value transform, they also, so the notebook itself is for quantum signal processing. These are related to each other. And what I did here, and I've used this in different notebooks with some success, is the angle is a parameter. So the angle is what makes this quantum gate trainable, i.e. this is the artificial intelligence behind it. And then this is the, you know, machine learning behind it, these types of things. This is what changes over time in order to give you a better, you know, accuracy, lower loss, these types of things. And so it worked quite well. So it actually said it dropped it from 0.5127 to 0.2863. And it's just one of these things. It's not 100% yet. So we have, you know, several papers. We have these demos. There's demos from other, you know, libraries too. And, you know, it's basically trying to find any which way to get better performance or faster runtimes, these types of things. Okay. Okay, so this next one is very interesting. So some of you may know this term. It's classical shadows. Now, as you may know, if you go to simulate, you know, quantum mechanics, quantum physics, and you know, on a CPU or GPU, you get exponential RAM depending on number of qubits. So as the qubits go up, so does the RAM. So this one, and I still have to research this more, but they say it requires just 3 NT bits, and this is those terms are in the demo, to be stored in classical memory if you use classical shadows. So, and again, so I included this up here. So for those that are not aware of using, you know, PennyLane, is you have functions. And this is basically, you know, it goes through these different, here's a parameter. Some are arguments, which are, you know, non-updatable or they're not trained as far as what's in the parentheses. And then in specific, you have this QML.polyx, you know, poly-y, poly-z. And these are familiar, they're called single gate operators. So they're, you know, quantum gates, they're matrices. And what was changed here is changing from a default.qubit to a lightning.qubit. So in default.qubit, 233 seconds compared to 208 seconds. When you can make the jump to lightning, you should do it. That's not always the case. Default.qubit, at least in these days, tends to be more compatible, especially it's or you're dealing with like TensorFlow and, you know, PyTorch and these types of things. There tends to be, you know, more restrictions on that. So that's the big thing with this is the RAM requirement for classical shadows. And it's doing things in a different way. And again, there's a lot more information in the demo with it. I just want to give you kind of like a briefer with this. So they basically, you know, it's a four qubit. So a lot of times, like for images, like for per pixel is per qubit. So if you're coming in with like a convolutional neural network with 4 pixels in that specific square, not the whole image, then that would be represented by a 4 qubit quantum circuit. So in this case, it's 4 spins, and then the qubits are attached to each, you know, so 1 qubit per spin for that specific thing. Are there any questions at this point? I saw there's a question in the chat. So, okay, so maybe we could come back to that, Ryan. I don't know if you're talking about Hadamard. And then Jack, let's say we basically multiply unitary. Jeez. Yeah, it's just it's a simple calculation. So Ron, if you could further clarify it, your question.
Well, I don't want to belabor this. I mean, they're obviously doing something that's more exotic than a single pass through the circuit. But your state vector is specifically, any specific qubit is going to have a state, and it may not be 1 or 0. So then when you measure it, the simulator has to simulate the collapse of that state to a measurement. That's a probabilistic distribution step. So, and that's why you have to run multiple. Part of the main reason why you have to run multiple shots on real hardware, not to mention the fact that real hardware has noise, but I'm just saying is you're going to find out that the state of a qubit doesn't wind up being in one of the measurable basis states. Something has to convert that via probabilistic distribution to a measurement.
Yeah.
So you can't do that on one pass. So that they must be doing something else behind the scenes. I'm happy to just leave it at that.
Okay, so this next one is very interesting. So there's two sets of experiments. So with this one, the first one is without quantum memory. And in this specific case, it takes a lot of shots. So 10,000 shots for this specific one. So the stock image, which is this random layers, it's part of the circuit function, the whole thing, is set to 0.3. And then you see the blue congregating over here, and then the yellow is kind of all spread out. So, a lot of times there's either, entanglement's not helping or it's slowing things down. And I think in this case, so I set it's called ratio and primitive. So it's basically getting the number of rotational gates are higher and the number of entangling gates are lower. So in this specific case, without quantum memory, you can see that the blue, consolidates very well. And then the yellow on the right side is basically, it's pushed off to the side. Now, and you look in the upper left-hand corner here, so with a little blue dot and then all of these yellows. So this is with quantum memory, like the model that they have in the demo, and it only took 50 shots in this specific case. And again, these are all done with just standard simulators. I think in this one, it's either default or I would have to go back to it, but it's set to shot mode in this specific one. So, you get this really good separation with quantum memory, with a fraction of the shots. And then, say if I optimize the circuit better for this case, I'm still not getting that separation. And it's like 10,000 shots compared to 50. So when you look at all these, you're looking for like, okay, how exactly can we use quantum where it really makes sense? Cuts down time, improving performance, these types of things. So again, these up here have quantum circuits, but no quantum memory. And the upper left one has a quantum circuit and quantum memory. So that was the big one with that. And a lot of these things are piggyback. So if you're familiar with principal component analysis, so kernel PCA, this is also with that. So you have, kernel PCA plus some quantum, addition to that as well. Okay, so this one is very straightforward. It's just making a tensor network circuit. So, or a quantum tensor network circuit. So the two big ones are called matrix product state, MPS, which I've done a bunch before. I've gotten over like 20 qubits. And this specific one is basically, there's a template in the demos. So you just simply look at the demo, and then if they have like 5 or if they have 4 qubits here and the next line is like 3, that relationship is probably like n-1. So you do the same thing with quantum, and all these things will likely be automated. It reminds me of like classic, they probably have gotten into tensor network or quantum tensor networks. But basically, tensor networks and quantum circuits have the advantage theoretically that you can run more qubits. So that's the whole purpose of these, is to get the qubits up, typically less entangling, and then more of these single gates. So there was an NVIDIA experiment where they got up to like 800 GPUs and say 1,100 qubits they got up with the circuits, and it was tensor network. It's this. So you're basically creating these new tensor networks to use instead of state vector. So state vector is traditional for that specific case. Now, on this one, what was just, so how to approximate number 9, a classical kernel with a quantum computer. At the end of it, it was, he put this picture up and they like, we did it, it was kind of like, it's a humorous, PennyLane sometimes does that in the demos. Very interesting, but I set, and I've seen it in Maria Schultz, some of her other demos, expansion strategy equals device, and it cut down on time, okay? So if you're new to programming and you're new to Python, when you look at all these technical documents, there's a lot of things, say in this case on the left, where there's these options, they're hidden if you didn't know about them, and then you simply change them based on your best conclusion of what to do. So on this one, you could set expansion strategy equal to this. I think there's one other choice. And especially if you look at QNode or QNode Decorator, there are a ton of options in there, to just, further try things out in specific. So it's basically, it's finding a quantum kernel that approximates a given classical one that could be posed on an optimization problem. And, it gets into these things, and there's theories behind circuits, and sometimes they don't work, or you could just do like a more straightforward approach. But basically that's what was aided with this one, is adding expansion strategy equals device, and then that's already kind of built into the left, but you just don't see it. Okay, so this is very interesting. So I know a lot of you are probably interested in GANs. I think there was actually a member who actually wrote, I don't think he's on right now. He's writing a thesis on quantum GANs. And basically it's behind this is you have these two networks, discriminator and generator. Now the generator creates this fake data, and the discriminator acts to see if this is true. So essentially, in a case like in medical, you could have 90%, or you could have 10% real images, like real medical images, like MRIs. And if this were accepted, then you have like 90% of it is just random noise. And over the course of running both of these networks at the same time, the noise starts to turn into images that look a lot like the real images through this. It's adversarial network. They're kind of against each other. So as you see at the top, these are actual images. I don't think this is MNIST. I think this is some other one. Some of these you have to download the actual data sets. So for instance, I bumped up the quantum depth, which is typically the number of layers you have in a quantum circuit. And then what I got is the generator loss is a lot lower. And then you can see the discriminator loss goes up. So I think that's the adversarial nature. So when you have lower loss for generator, you typically get better quality images. So the images on the right here more closely represent the images on the top. In terms of, I think the main thing is just white versus black. You can see maybe accuracy is not 100% there after 500 iterations. And on the left, the stock model, in the notebook, you can see it's very, it's not as good as it, after the change was made. So awesome. So any questions at this point regarding, so a lot of this is pulling in regular machine learning, deep learning, neural nets, all these types of things, and now incorporating with quantum data. Now, on this specific one, I don't think you can do a quantum discriminator at this time. So the quantum circuit was in the generator in the specific one. And then, so here's the next step. So this is very interesting. So it's about unitary designs. And it's basically saying you're able to compute the average fidelity on these 24 experiments using these single qubit Cliffords. Okay. So in other words, there's things that take too long, or there's just better ways of doing it. And this appears to be one of them. So this first one is just, it's a blank between it. And then the rest of them account for the 23. So as you see here, so I changed the flip probability for this specific case, and then all of the fidelities went up. So that was just one of the parameters that I could change, is flip probability. And it's basically, if you're talking about, do you have to determine the full Haar measure, for it to be sampled, those types of things. Now, this one also is interesting. So this is number 12. This is training and evaluating quantum kernels. And on the left, so these images are kind of cool because sometimes they're they look like things that you might recognize in real life, maybe like a lake and some sand on this one. And everything is looking good in this left one, except for the red dot is not in the red landscape. Okay. So that's the issue with that one. So I changed the CRZ, which is a control RZ gate, into C knots, which are, 2-qubit gate as well. They substitute quite well. And then on my landscape, I got this. And for this one, that's all I had to do. You'll see they try to get functionality with scikit-learn a lot. So you'll see scikit-learn in a lot of these different models, or a fair number of them. But that's all that really took for that one. So it's a broadcast function, which is basically it can slow things down if you're not careful. And it's just one of those options you have to change. You can change, instead of doing CRZs, a different 2-qubit gate is a C knot in that specific case. Okay, so 13, understanding the hard measure. So the whole point with this, I couldn't initially get like tables. So it just outputs these. So this is the left, the best case they got. I think they updated it 3 times throughout the demo, and this is the end. It's trying to do expressivity. So basically you want dots to be all across the qubit. It's a representation. And then you see the one on the right. So I've had luck with these modifying the variables. So like a 5-1, omega +1 was the closest that I could get. And a lot of the times you have to keep running these experiments, to get to the end. So they're pretty similar, like I would say they're both, they have a lot of concentration of dots around the edges of the qubit, which I think is normal. And that's the tricky part, is basically to pull it down. And the whole thing in literature is it'll have the statement like, assume that the unitary is sampled uniformly at random from the hard measure. And this is related to that. It's basically trying to get these, better expressivity. Okay, so for this one, so you could say, oh, atom isn't quantum. Well, it is. it's hybrid, right? So when you're running these models with, atom optimizers, I tried a bunch of the quantum specific ones, but I couldn't get the outputs to match up. So I, run one and it says error, just there's some error, like the optimizer cannot be used as a replacement in this specific case. And basically it's expected if you increase your learning rate that you will decrease the time. And in this case, I didn't really suffer much. You could see the landscapes are a little bit different. So for instance, like this one is more towards the center, more favorable. But when it did its final loss, they came out to be the same. So in other words, sometimes if you want to go faster, go into optimizers, increase learning rate, if you're not losing much with fidelity. So it's just it's what your end objective is with everything. And and again, the demo in this specific case, this LSTM recursion neural network did better than the standard stochastic gradient descent. So, it's if you do things quantum, can it be slower? Can you get better accuracy? You're kind of like weighing these things. Are there any questions at this time with, so we're on 14. And then, so this next one, so again, like, I think when researchers do a lot of this work, it's very time consuming. So you have templates. So templates, such as strongly entangling layers, this is on the far end of, it's essentially like fully entanglement, that type of thing, if they're dealing with that with like Qiskit. And in this one, I couldn't change the ratio of, say, like rotational gates to entangling gates, but I could change it into a CZ. So I believe the one on the left is strongly entangled. So that's a template. And on the right, so this QML.ops.cz changes things. Okay. So a lot of times, if it's at step 100, the loss is 0.420. Over here, it's 0.406. So the accuracy is still showing similar, but you could see if you were to take this out much farther, this loss is still trending down. I mean, it's still got a curve to it, but maybe kind of flatlining here. But this one for sure, it's not going to go down much further. So these are the types of things, these substitutions. And in specific, this one is comparing kernel-based approaches versus variational. And the big thing is if the variational circuits in many of these things have a high number of parameters, it's likely that a kernel-based method would be faster. And then on the flip side, if the variational circuits have a low number of parameters, it could be that they're faster than kernel methods, right? So it's kind of having this knowledge and where you're programming with all these things, and kind of where you're going. Okay, so number 16, turning quantum nodes into Keras layers. So these are extremely helpful, it appears. Okay, so this is TensorFlow, this is Keras, and you're basically inserting. So I included a clip here. It'll say C layer 1, Q layer 1, C layer 2. So first you have to prepare this QML.QNN Keras layer, and then it has to be in this form. So essentially you can run this, with, default.qubit or any other simulator pretty much in your existing workflows with, TensorFlow and PyTorch. Now this specific one, it was significantly faster, or I'm sorry, it was significantly slower than the PyTorch. So I'm talking about deep learning right now. So deep neural nets. So say for instance, like one layer, is classical. The next layer you want is quantum. The next layer is classical. And it's just up to your imagination what you want to do with these, as long as they're working. So like I said, this one tended to be slower. And in the TensorFlow one with C, it says having an argument called inputs. So on the Torch one, I think it's a little bit more streamlined. And so this is 16, and then 17 is with Torch. So with the Torch one, I added 2 more quantum layers. So you can see with here, they start off with it's C layer 1, Q layer 1, Q layer 2, C layer 2. And then I added 2 additional. So I now have a Q layer 3 and a Q layer 4. Got better accuracy as was expected. And then the average loss is lower, right? So that's what you want. Lower loss, higher accuracy, that's the case. And so this is the harder of the two. So if you look in the upper left-hand corner, this represents basically it's a snip of the function here. So classical layer, 2 quantum layers, and then classical layer here. The first classical being, this torch.nn linear, and then softmax function at the end. So again, when I go to a lot of these meetups, I just get that kind of like, oh, you can't do much, or I think you can. I think it'll strongly accelerate once, the killer apps comes, whether it's, simulators or hardware. So that's the crux behind that. So again, for those just joining, it's adding 2 quantum layers, decreasing loss, increasing accuracy. This is 17. Now, 18 is interesting too, because a lot of these papers, so say for instance, it's a trainable layer, which is represented by W on the left, and then an embedding layer by S, and then a trainable. So this has worked for me, but not in this case. So I actually did the traditional route, and I went embedding to trainable layer, and then my cost was down by an order of magnitude. So the blue line is what you're trying to fit to, and the dots with the the blacks is your after running your quantum circuit, like how close does it fit. So this is part of that. They call it part 2. Okay. Any questions at this point? And then feel free, you could also raise your hand. You could also put in the chat too. But I guess the moral of the story with this is, sometimes these, you'll see alternating layers between embedding, trainable. And in this specific case, the more traditional route, which is just embedding, like that sees the data first into trainable. So there's different ways of doing things. It's just important to know that. Awesome. And then 19, the quantum graph recurrent neural network. Now, the image you see on the top, the left image where it says target is the actual image. The initial is before training, so before actually doing, running the demo. And then the one on the right is learned. And you can see that they're pretty close. Okay, so you're looking at the left image and the right image. So I mostly look at that yellow dot, and this one on the right is just off. It's just, it's just brighter. So it's not 100%, and it wasn't expected to be. So on the left, the stock setting was step size is equal to 0.5 for Atom Optimizer. And on the right, I changed it to 0.3, which would make things, fine tuner, which would make things, run slower. And then it gives you a printout, and this is the first time I've seen it in a demo. So 6 of the weights and biases associated with this hybrid network were closer for changing the step size, making it lower on the right. And, there's this one I've run ad nauseum on my own. So it's using the MNIST data set. So it's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's 10 classes. And if you run it with 4 qubits, and actually this is from their notebook, this is what they got. It varies a little bit on this one. Not every time you run these is the same exact thing, depending on the demo. It just depends. So you can see the classical had higher accuracy than the quantum with 4 wires. Now, the only thing I changed was I went into and I said double the wires, and you can see this blue just shot up significantly. So this is not the end all, meaning that this isn't like the permanent solution to getting, a better quantum convolutional neural network, but it's a good step forward to understand that, hey, more qubits, yes, it will run slower, but in this case, you see the blue line, creep up significantly in that case. And so it's basically a CNN, it's a convolutional neural network, and the part in the graphic in the upper left-hand corner, these are basically the pixels themselves. Like I said, like if you have 4 pixels, 4 qubits. So in a different demo, 4 spins, 4 qubits, these types of things. This one is very interesting. Okay, so this is called Ensemble Classification. Now, what Ensemble Classification does, and you can see they used a Rigetti simulator, they used a Qiskit simulator, and you get values on how well you run them separately, and then you get values of how each of them do, and then you have an ensemble model. And the ensemble model for these two on the left, one of them was low because some of the simulators or some of the these functions, and they're running in simulators, they have a preference towards say if it's 3 classes, they'll have a preference towards if it's like a stone or a rock, that it's just better at classifying that thing, as you may imagine these types of things. So anyways, it gives you a ton of data, and the end result is basically I switched over to default.qubit, and then I also switched to circ.qsim, try something different. And these are all the same. They're all 4 qubits. They're all same circuits, the whole thing. So as you can see, the ensemble classification on the right did a little bit better. And I also had some time issues running the Rigetti. And then after I looked at the notebook, you have to do some additional things with that to do that specific simulator. And then, so it worked out well, basically switch it. So default.qubit is PennyLane's, circ.qsim is Google. Now on the left, a Rigetti, that QVM is a Rigetti, and then Qiskit is IBM's quantum simulator. So in a sense, they're kind of putting them head to head, but the way they phrased it was like, it could just have a preference towards a single type of, usually one will have a strong preference for one. And anyways, it's you want your accuracy to be higher by doing these duo, and you can go into like multi whatevers just because one favors a certain class in a data set. Any questions? And you also have to load this too, is this params.numpy. Now I would say maybe about 5 or 6 of these demos, you either have to download the data set, which I've done with an upcoming one, this one, okay? And I'll have the full kind of printout of this a little bit later. But basically it's using transfer learning. So where it starts off is in the left. Okay. So before you even think of the model, in transfer learning, you're getting these weights and biases from a pre-trained model, say a ResNet 50. Okay. So you're taking that, and then now you're doing that again, but with a much smaller data set, your training set. And then as you can see in the middle here, this is how it breaks down. So for instance, data would go in. Actually, it's not an image, it's an element. Okay. There's like for ResNet, there's 512. Goes into ResNet, and then those 512 go into 4. Okay. So 4 represents the number of qubits in the QPU here. And then from 4, gets measured, and then it goes into 2. So 2 meaning an ant or a bee. So what's different about this one is the QPU. And the simple thing that I did is I took out entangling layer, and you could see, so it made it faster. So 1 minute 12 versus 1 minute 20. It also decreased loss, so 0.44 minus or compared to 0.41, and then an increased accuracy as well, 86. Now that this might not always be the case. So a lot of times the entangling seems like, bigger problems, those types of things. And like this is only like 300 images. So, and the entangling slows things down a lot. Are there any questions or comments at this point? And you could feel free to raise your hand. And then this one is basically, it's a photonic quantum computing. So PennyLane uses, it's called strawberry fields.fock, and they had a cutoff dimension. It's the number of photons going through, okay, of 10. And then so I changed that to 15, and it worked out in the favor of cost. So it's basically some of these, some of them, as a whole, the graphic on the right to me appears to be like, if you look at this N blue here, now it's included in the function here, or it's fitted. And, you just kind of analyze it like maybe this part's better than over there. But at the end of the day, it has a lower cost function. Overall, it fits the data better in that specific one. And then here's another GANs. So like I said, GANs is really popular. And all I did on this one, I stayed Google. So it went Google Circ.simulator to Circ.QSim. Now, Circ.QSim is interesting because they claim it's the simulator that went up against quantum supremacy in October 2019 for that Nature paper. So they say it doesn't click in until maybe like 15 or 20 qubits where you really start to notice the difference between these two. But it depends on the task, because it decreased the time from 47 seconds down to 29. So, part of this is experimental. Part of it, you're reading off documents and say like, okay, I'm going by this chart, and it says like exactly, 15 or 20 qubits. Then I'm going to switch over to Circ.QSim. And then, this is maybe an outlier to that. So here's 25. Now, data reuploading, you can do with, say, like 1 qubits or 2 qubits. Now, when I think of data reuploading, I think of a single wire, or like a Qtrit, Qquart, or 10-dimensional QDIT. And you're not missing out on, or basically you're avoiding all of this RAM, exponential RAM, and exponential time, these types of things with this method. Now they use qubits for this, and I had previously run this notebook, and the only thing I could find that helped was this adding a poly Z before. So QML.rote is the same thing as like a RX, RY. Well, I shouldn't say that. This one's star X, so it's over the X axis, and then it'd be trained, right? So it's trying to find that optimal rotation to get the best, accuracy. And then on these, so yeah, cost was lower. And that how it shows up in real life is the one on the left, like, the data, it says predictions with random weights. Now, the ones that the ones that matter the most are after training. So you can see the top one is more centered towards the middle, like a bullseye. Okay. So this one is the one with the modified circuit, like lower cost, matching to the bullseye. And then this bottom center one is basically, it's more pancaked. You see, it's more elliptoid than that. And the whole goal is to get it to match up, right, like spherical, like that. And then this has been recommended to me to run this and to modify it, make it my own, or, write a model on it. Variational Classifier by Maria Schuld. And it goes through all the steps. And I think why they recommended it to me, because quantum transfer learning to me is more, it's got like a residual network. It's got quantum. There's just more going on. This is more of a step-by-step. So Variational Classifier, I would say. And I just increased the layers to 8. And at lower iterations, I got this lower cost. Okay, so 0.27 compared to 0.3. And I think the big takeaway here is you'll hear that term linearly separable. So on the left one, you see that the curve, is more like this. And I would say where it really messes out is up here. Okay, so these red dots compared to this are much farther from that line. And then, even down here with the blue, this first blue dot is farther from that. So this is all represented by the cost function of that specific one. Now, are there any questions regarding any specific demo that you'd like to talk about, or how to get started in PennyLane?
So Kevin, you started at the beginning. I think you mentioned you were using Colab. Were you able to run all of these examples in Colab directly?
Yeah, except for one, I had to run on a Qiskit notebook. So it's just the time and trying to get all these, you can run a notebook, but it takes another level to, either get faster times or better accuracies. For the most part, I really like Colab. You start off with a fresh slate every single time. Like I'm having an instance on my local computer because of, different things being installed, and it's like network X or something like that. With anything like these cloud notebooks, they're number one, other people can hop on and code with you at the same time. But I like them because it's like nothing's installed. Like say for instance, all of the neural networks they have. Okay. So if I want like a 2 gigabyte, monster, like a Hugging Face on my computer, I have to store that. So that's a huge thing. But as far as like, I like it because, it's just, I pip install PennyLane every time. There's nothing like, say for instance, if I ran virtual environments here, that would have been wiser, 3 months ago, as opposed to there's something going on. But yeah, the cost of CPUs are really low. It's like fractions of whatever, and I think for a V100, you're looking at 50 cents an hour, an A100, like $1.30. I didn't do a A100 at all. I think I used V100 once or twice here. So did that answer your question?
Yeah. So when you're doing it through Colab, are you doing most of it as a local simulation? And is there I assume there's some mechanism where you can eventually run your circuit over on Xanadu's stuff, right?
Yeah, well, you just
either their quantum processors or their monster simulator over there.
Yeah, every time I complete a run and I want it, most times I save a PDF, and I'll also save the Python notebook. You can also save, let's see, you can also save as a script. So you can save as a .ipynb or .py. And to me, this most straightforward thing would be to take that Python notebook .ipynb and then go ahead and run it Xanadu or whatever. Like once you have the notebook, that's kind of how I'm doing things. I'm not like, because with Colab, once you're disconnected and deleted from runtime, you're not charged anymore. And also it doesn't store my stuff. I think there's ways of doing that, like if you bump up to cloud, but I have an efficient way that's been working. Mostly it's just saving a PDF and then saving the actual notebook.
Right. So just by loading the PennyLane framework, you have access to their simulator that will run their code, so
Yeah,
to
so
speak, or their,
yeah, for instance, if you want to launch one of these demos, is that it likely has everything you need. Now, if you want to
yeah,
tinker, go to default.lightning.qubit and those types of things. You'll start to have to understand like, the what all you can modify with some simulators. And say, for instance, if you want to jump up to lightning.gpu, which is like NVIDIA GPUs, you have to go through a couple steps. And I actually think the code itself, depending on how many GPUs you have to write an additional line of code. So I think a lot of these people, in classical world are just very familiar. And I had reached out to somebody at NVIDIA. I said, yeah, this is beyond me. Well, it turns out you also have to pay for it too. So and I think that they switched to pip install for cuQuantum as opposed to like Dockers and these types of things. Things are getting better.
okay. Yeah. But again, it all will run within Colab unless you want to link it out to Xanadu's resources, right?
Well, yeah, it's actually simpler than probably what you think. So even if you
Okay.
use like Xanadu or a Briquette or whoever, I think the only thing you have to do is when you queue up, like say for like, I know for Briquette because I tried it. So say your user ID is set in your device for the Briquette, TN1 or SV1 or whatever. Now, every time it queues that up, Amazon knows that and you're billed. Okay. So I think they've gone to lengths to make it easy. There's just
Okay.
things to be aware of, especially like, it's always going to be more complex going to a GPU. However, a bunch of these notebooks, like quantum transfer learning and others, they have a CUDA line. So if you're set to a GPU in Colab, it senses that in the notebook, and then just that's how that works. But I think though that even with Amazon too, I think it's just simple. I think it's just like as long as you have that stuff figured out with Amazon, the line with the simulator is it has your user ID or something that ties it so it knows when it's running that simulator, it's charging your account.
Yeah. Okay. Sounds good.
Yeah, it's not that hard. It's just you have to discover it out. And if you have questions, anybody else have questions too, it's just one of those things. I would say a lot of people coming from classical programming now switching over to special Python functions, i.e. quantum circuits. I watched a PennyLane thing and they said it was harder on the deep learning end than it is on the quantum end to develop some of these models, just because, the level of complexity is still mostly classical. But, understanding quantum physics and to change your circuit or double layers and these types of things can help. But that's when it'll really take off, I think. I went to another meetup this past week and they're starting to buy into it. Like I read this as an API and I sent them that torch demo, and it's very straightforward. It runs fast. I don't know how just there's a queue in front of things, change the gates if you need to. You usually don't come across too many exotic gates. Awesome. So anybody else that we haven't heard from? It's exciting stuff. Go ahead, George.
I got an email from, was it Xanadu, saying that these notebooks were going away. Did I misunderstand that?
Demos?
It's, hold on, let's open that mail.
I think he said notebooks. are going away.
Yeah. I mean, I wonder if that's like gate model or something else. But yeah, you could fill us in. Anybody else we haven't heard from? So Andres or Diego? Maybe some returning people here too. Dave or Javier?
Nothing for me.
And then, we also have Dino or who else? Or Matthew?
This said something, only 14 days remaining to download your PennyLane cloud notebooks.
Oh yeah.
Oh, that probably has to do with their free tier is ending or something.
Yeah, like your personal note. I don't think those are demos.
Oh,
I
okay.
think they
Thank
love
you.
demos.
So
I'll turn my head and there's a new one.
Yeah, IBM Qiskit is starting to do something similar. If anybody here who's played with the IBM Quantum Challenge, their IBM Lab and their IBM Composer, that's a free tier thing. You can get into it. You get access through that free tier. You can get access to 5-qubit machines. IBM is going to start depreciating those 5-qubit machines. They're going to be rolling out bigger machines. But they've also start encouraging people to sign up for the Qiskit runtime, which is their cloud service. And that part's a little more complicated, but I assume that the lab and the composer will just slowly behind the scenes be switched over to the Qiskit runtime, and maybe you don't have to worry about it from that side. But if you want to run bigger programs, you'll have to learn how to do it in the Qiskit runtime environment, which is another login. You can use your same credentials, but it's another login, and you have to give them a credit card. You don't have to. There's still a free tier over there, but someday that may go away too. So
Yeah. Yeah, I mean it's I'm on most of these channels and I get asked, can you help us log into IBM? Because I tend to help people out there. And I mean, my approach, what it looks like is most of the QML stuff is pretty well being developed with PennyLane. And then I'll also need, Qiskit, SERP or, QSIM simulator, these types of things. But I would say they have, these are like the first waves, like with these QMLs, like even like this quantum transfer learning, it's a couple years in my mind ahead of its time, but there's still many things to either improve speed or, better understanding of which exact algorithm. And you can have like just stuff that you didn't even think about, like for this specific image in this specific data set, the qubit now recognizes or qtrit or whatever, and then it treats it differently than our current understanding. Like what's interesting about the demos is the kernel methods versus variational. And they said that for variational quantum circuits, which is what most people run, they are favored, at low parameters, and then kernel methods for higher, parameters. So, that's the demo, right? It's not like taking the next 20 steps into further optimizing. In my opinion, these are the ones that we'll likely see. So I think there's a lot to look forward to in programming with quantum.
yeah, you should keep your ears open for a company called QEra. They're going to be bringing their neutral atom stuff online, and there's so many cool things you can do with that, and they are definitely going to be making inroads into QML based on some of the things I've seen over there. It is new hardware, so it's going to take some time for them to flush out all the issues and stuff, but you have another dimension of programmability with the neutral atoms, and that is that you can arrange them part of your quantum algorithm could be to arrange them in whatever pattern you need.
Yeah.
It's like IBM's superconductors. They're fixed on a circuit board somewhere, and they can only talk to the other qubits that they have waveguides to. Whereas with these neutral atoms, if you want 6 of them to talk to each other, you just move them together.
Yeah.
It's pretty cool stuff.
Wow. So you could actually instantiate a small neural network qubit by qubit.
Almost, yeah. But what their big example was, they basically align the physical locations of the qubit inside the chamber to match a real world physical map, like pinpoints on a map of Boston, because they like Boston. But so what happens is that instead of having a regular spacing, every pinpoint on the map, if you could just imagine the map of Boston has a pin that has every coffee shop in it. So it's going to be this weird array of pins. Well, you can make the qubits in their machine look like that array. And then now you can do calculations based on the distance between the neutral atoms. It's really cool stuff.
Wow.
Yeah.
Yeah.
That sounds really awesome.
I definitely see some applications for quantum hardware for specific applications, not like running in hybrid notebooks. So say, for instance, like you have a training set, and the only thing you care about is the end result. So yes, there's noise and whatever, but the probable benefit of having more qubits, faster speed, speed is a huge thing in training networks, and say the accuracy of that training model is better than what was before. Now, for inference or validation or testing, where the risk of basically, having an individual image that's misanalyzed or, misclassified is of great importance, that might be more on the simulator side. But that's not without, I think that's within reason of thinking that even though you have all of this noise, that, having the big circuits and the speed, and basically the only thing that matters really is the end result, meaning these are your weights and biases to now use in inference, right? So I think there's probably ways of overcoming that, with noise, but these things are, they're within reason, right? Anybody else? Any other questions or comments? But yeah, that's the way things are looking at it. I'm sticking with QML and, getting support with the kind of the other platforms. But I think they have a kind of, with these demos, especially, a head start. And quantum machine learning, they say, is going to be the principal component. I saw, was it $5 billion, most are 30% compound annual growth rates by 2030 for QML. So it'll be interesting. Awesome. Any other last questions or comments?
Kevin, a couple of my colleagues are wondering how they get on your invite list for your sessions.
Which one?
On LinkedIn?
Oh, anybody can join, and then I get 600. So, yeah.
You can join the
it's all word of mouth now. So, the startup and where things are going. But I think
no, I mean, I get an invite from you for these sessions on LinkedIn.
Yeah.
So
I only have
assume
like
you have some.
Go ahead.
So I assume you have a list somewhere.
It's somewhat tailored to topic, and right now
Okay.
it's a lot of programmers, that type of stuff.
So if we send you, I'm already connected to you on LinkedIn. If we send you a note on LinkedIn, you'll send us those invitations. Because I found this on Meetup actually, and I registered for it on Meetup, and put up the thing, add this to your calendar, and I did that. And then this evening, when I went to the calendar, it gave me a link that went back to Meetup, and it said, registration is closed, link is only available to those who registered. What?
Yeah, once you're in, you're in. What I do for LinkedIn is whoever attended last session, I automatically include in the next. Like I always do that. I'll also include maybe like 2 or 3 others, like 2 or 3 other people that registered on LinkedIn. But yeah, you should get that on Meetup. But yeah, it'd say, if you're on LinkedIn, it's probably more foolproof.
I'll just send you a quick note on LinkedIn to have you
Yeah,
add me to your
LinkedIn's
list.
a lot easier. A lot easier. It's just there. You click on it, you're here. It's
Yeah,
cool.
yeah. Any other last questions? I forgot. If you didn't join last week, there's one of these. I'm all Linux now. It's just, some of the things aren't as
As you should be.
yeah, it's literally my name desktop. Okay, so okay. So yeah, that's to get you started. Now I get that sense that maybe many people haven't run a ton of demos here. So the one last week and also the YouTube for last week too, you can follow along. That's really helpful, right? Because that helps me learn what I can teach and I can helps me develop too. So I just put that in the chat, that PDF. Definitely check that one out. And if not, this has been, whoa, this is 98, huh? Yeah, discussion 98. This is Thursday, August 31st, 2023, for all PennyLane Python Quantum Machine Learning Demo Seminar. Have a good rest of the night and have a productive rest of the week. Take care, everybody. Bye.